We are recording. Okay, so welcome back to Runtime School. So this week we're doing our first week on Realm. So this will be the first session talking about the Realm runtime, which is the runtime underneath of Legion. Before we start, Manolis asked me a good question offline last week about what sort of the motivation of the school is, and one of the things I think that I should have clarified last week is that the goal of these sessions is more to explain the theory behind how these runtimes are supposed to work, how Legion and Realm actually work and should work. Like, I'm not going to dive through every line of code. There's way too many lines of code to explain in detail everything that's happening. So, what I want to accomplish in these talks is to effectively give you the theory of how things work, and then that'll allow you to have a framework in your head of, how things should work, and then you can go look at the code and understand what it's doing conceptually, right? And then see how that maps to the actual details of like what the code does in practice. So like I said, I think, these sessions are not sufficient to totally understand everything that's happening, but it provides the framework to ask further questions, investigate the actual source code, and understand what's happening in practice. Okay. So with that, let's dive into today. So Realm sits, under the runtime folder in the repo, and there's a whole bunch of subdirectories and stuff for different submodules here, and we'll talk about modules and similar things later. And then the rest of these files are all part of what we consider the core Realm runtime. So what I want to talk about today are events, because events are pretty fundamental to how Realm actually works. Pretty much everything in Realm interacts with the event code in some way or another, and that's it's going to be a vital thing that we understand, like conceptually, how events work and how users use them and how they work under the hood. So let's actually look at the event.h header here real quick. So this is the base event class. Effectively, events are just handles that you figure out, or that you can use to signal when something has occurred, right? So lots of things in Realm will give back an event that will trigger once some asynchronous computation or event has occurred, right? And then you can chain events together and merge them together and to create new events and then pass them as preconditions to other stuff in Realm. So events are really the glue that holds everything together. As I said, events are handles, which means that they're just like a lightweight name. So like you'll see that this class actually has only one member variable, and it's this ID member variable here on this line. And we'll look at what that ID is and how you interpret it and stuff during this talk. And then there's a whole bunch of methods in here for merging events together, for waiting on them, for checking if they've triggered. We'll talk about what subscribe does, and you can even cancel and poison them. We're probably not going to talk about that part today. You can merge them together. There are also other variations on events, things that inherit from event, right? So you can also make a user event, which just is a way to say, like, this is an event that the client is going to be responsible for triggering. So it has all the methods of the normal event plus a trigger method or a cancel method that you can, either poison or trigger the event with. Realm also has barriers, which I don't think that we're going to talk as much about today, but I'll at least mention them for completeness here. Right? A barrier is just an event that triggers once it gets a certain number of arrivals, right? So you can effectively have multiple, if you want to think of an arrival as a kind of trigger, right? It effectively says, you need to have many arrivals before the event actually triggers, right? Unlike normal events, and our own barrier is still a handle, but it has a little bit of state in that, effectively it assumes that you can trigger multiple generations and stuff. So we'll probably end up talking about barriers at some point later. They're a little bit more complicated. And Realm also has this thing called a completion queue, which is an efficient way to test whether a whole bunch of events have triggered. So you can effectively add a whole bunch of events, right? And then you can sort of call this pop method, and it will give you a fast way of testing if which events in a set of events have actually triggered. Legion actually makes pretty heavy use of that in a couple places. So, but today we're going to focus on this event class here and probably the user event, since we'll want to look at how things trigger. So the first thing I want to do is just take a brief look at what happens if you're running inside of Realm and you call wait on an event. Okay. So what you'll see is the way to find these methods. So we're going to go find out where event wait is. what you'll see is that Realm has this sort of a convention where there's like a header file for the public-facing API, which is this header file for event. And then there's also a header file for the implementation. So if we go look at event impl.h, this will actually show you some of the internal versions of these methods. And actually, let's see. I'm actually in the right thing. I actually think it might be event.inline is what I'm actually looking for. Let's see. Yes, sorry. Let's actually go look at event.inline first, then we'll look at event impl.h. So if we look for, let's see if I can find wait in here. Maybe wait is actually in event impl.cc. Oh, yes. So there's just a few. You'll see Realm has a bunch of, anytime it has an inline file for some of these inline methods, like for testing, like event, whether one event is less than another equal. You'll get those in the inline version of something. And then impl is like the internal implementations of Realm stuff that is not supposed to be user visible. So we can actually look at event impl.cc here. And if we search for event wait, here's our method. Okay. So if you call wait on event, what this is going to turn around and do is actually call wait fault aware, right? Realm has, you often want to test whether, an event is poisoned or not, right? So wait fault aware is also a user facing API that the user can call to test whether the event either triggered or was poisoned, right? With the common case being that usually it triggers, right? So event wait is just turning around and calling wait fault aware, right? And so, first off, every event that has an ID of 0 is what's considered the no event, right? And no events are trivially triggered and always ready and stuff like that. So, if your ID is 0, that's our no event, and that's what we have a special test case out for that simple case, right? And the next thing that happens here is we actually need to get the internal data structure that actually represents this event, okay? So we need to find this event impl. And what Realm is going to do, the first thing it does is it gets its runtime. And we're going to do a brief digression on how this works to get this event impl and how we actually get this data structure that represents the event, through these two methods, and then we'll come back here to this code and look at that. So let me actually start a new tab here to take a look at this. Right, so if you just remember here, we're going to call get runtime first. I'll show you where to find that. So if you go into Realm and we find runtime impl.cc and we search for get runtime, right? Okay, so Realm has a static singleton runtime object, okay? And it's this, you can use this Realm : get runtime, and that gets you this implementation, right? And then you can return that object. And this runtime object, if we actually look in runtime impl.h, let's see here. Here's our runtime impl. What you're going to see is that it has a whole bunch of these tables for looking up various different things. So it actually has this set of nodes. I'm remembering how all of this works. Right. So you see that this runtime impl has this node data structure. And what this is doing is it's tracking, on any given node inside of Realm, this node's data structure is going to track all of the nodes that this particular node has received like a reference to from some other node. And what that means is like if the user waits on an event from a remote node on this local node, what we're going to do is like have to have some way of representing what we know about that particular event from the remote node, right? And so we need a data structure to handle that. And this is true of all sorts of things in Realm, including like events and reservations and sparsity maps and index spaces and all sorts of things like that. Okay, and so effectively this node data structure, and I think it's in this file. Maybe it's not. Maybe it's somewhere else. I have to apologize. My Realm knowledge has. Oh, here it is. It's a struct node. My knowledge of Realm has shifted a bunch as Sean has refactored stuff, but I still understand conceptually what's happening. So anyway, here we go. So you can see this node data structure keeps track of a bunch of different things that it knows about from the remote node, right? So it knows about memories, IB memories, which are intermediate buffer memories, processors, DMA channels, remote events, barriers, reservations, completion queues, right? All sorts of things that can be referenced from a remote node, right? And the important thing of this is data structure is that it's populated lazily, right? So we don't eagerly like hook up all these things. So like if you make an event on one node, that doesn't mean that all the other nodes have to know about it, right? It's only filled in on demand as as Realm sees references to like an event on a remote node, then it will populate this data structure, these data structures on demand with what it knows about those things. And we'll talk about what some of these dynamic tables and stuff and how they work later, but effectively they're just ways of lazily instantiating data structures to represent things like events and reservations and so forth. So if we come back and look at, let's actually jump back here. Let's see. Can we jump back to runtime impl.cc, I think? Right, so we got our runtime. Right, that gives us our runtime singleton. I'm not showing you where this like realm get runtime. You guys can go look that up, but it's effectively just understand that this is just giving you a singleton reference to this runtime impl object that realm keeps around, on every process for the duration of its execution, and it's a thing that manages all the state for all the different resources and stuff that node knows about.
Mike, I have a question.
Sure.
I was wondering, is there a reason why it's like in Legion stylistically, there's like a runtime meta object that all the Legion things take in a runtime, or like if you use a runtime to dispatch, like is there a reason why Realm doesn't do that?
Realm doesn't have a concept of a context. There's no hierarchical stuff. I guess one way to think of it is Realm does everything with handles, whereas Legion has an explicit state because there's some concept of like hierarchy, or there's a task hierarchy in Legion, whereas in Realm there's not, right? So I guess it's just a matter of stylistically, right? I think Legion could probably actually transition to the point where like it's more similar to Realm, where we did more things with handles and used like we would need a little bit of like the. Yeah, I think Legion could probably actually get rid of the runtime dispatch and just dispatch on the context handle, but we would still need the context handle because like that's a concept, that like the concept of hierarchical context in Legion is different than anything that exists in Realm. Realm doesn't have that structure to it, so yeah, it's mostly stylistic.
All right, makes sense. Thanks.
Okay, so we got our runtime. So when you see this like get runtime call here inside of wait fault aware, that's just getting you the singleton runtime object, and then what you're going to turn around is ask it to look up the generational event data structure that represents this particular event. So if we search for get event impl, right? So a little check to see if you're shutting down. It's very bad to be looking things up after you're shutting down your Realm runtime, right? The next thing we're going to do is look up this ID. We'll go look into what this does later, right? It then checks the type of this ID. It checks it if it's an event, it gets you a generational event data structure. If it's a barrier, it gets you the barrier implementation, right? And otherwise, it says there's an invalid handle. And we'll see how you determine that this ID is an invalid handle actually right now. So this ID concept is something that's very important to Realm. And you'll actually see that this concept of an ID is used everywhere inside of Realm. So an ID is just like, a handle for representing some resource that the user can pass around by value anywhere inside the machine, right? So like an event is just this ID is just I guess normally on like 64-bit machines, the ID is a 64-bit type. In fact, I think it's 64-bit types on all machines, even on 32-bit architectures. I think we've defaulted the IDs to 64 bits, but effectively the user can pass it around by value, and the ID encodes all the information needed to represent, for Realm, how to look that up. So let's actually go take a look at that, where that is. I'm actually going to start a new window here to go look at that ID. So jumping back to Realm, and we find id.h. Okay, yes. So here's our ID class, and you see it's just one of these Realm ID types, and the documentation here is actually pretty good. It says that all these are 64-bit values that encode IDs, and so you can actually see how to decode these IDs. And there's a bunch of helper code here to help with this in this class that I'm not going to dive into right now. The important thing here, though, is that you can actually tell from any 64-bit handle inside of Realm what it is, right? So the first thing you can see is a tag, right, that says how many bits it's needed to like it's sort of like a type tag, right, to say what kind of type this handle is, right? So when we look at like this code right here that's checking like, is this ID an event? Well, that's really easy. You just look at the first bit, right, and see like, you know, if it's set or not, whether like in this tag, whether or not that's an event or not, right? And similarly, like you can look at pretty much, you can see Sean is using kind of a dynamic, you know, number of bits here to represent these types, right? So that common types are actually represented quite simply with fewer bits, whereas like less common types have more complicated, require more bits to represent their type. But effectively, there's a way to decode this and say like, you know, based on these tags, you know, is this an event or a barrier, or reservation, or memory, and so forth. And then after that, you know, there's some bits in here to represent, you know, the creator node, which node actually made like an event or a barrier or reservation, or in the case of like memory is who the owner node is, right? In the case of events, you also have to represent, you know, the generation of that event, and we'll talk about what generations are a little bit later. Some of the barriers, you have barrier ID, like barrier indexes. I guess, sorry, I'm getting a little ahead of myself. This gen event IDX is actually saying which generational event data structure is storing this, and then this is the actual generation that's being stored there. Or how many bits there are for being stored, right? So, and if you add all these up, it adds up to 64, I'm pretty sure. 47, yeah, 64, right? And so you can see there's also some unused bits in some of these types and stuff like that. But anytime you see like a weird hexadecimal number in a handle from Realm, right, this is your decoder table to help you figure out, you know, how to reference this thing. And I'll talk about how we use these bits to look up a data structure in the case of events right now, but the same principle is going to apply for lots of different things, like pretty much any kind of handle that you can get in Realm, right? You can decode these bits and use that to figure out, you know, what data structure is actually representing these things, right? So let's actually go back to this class. So we're going to go down this case of if ID is event, and the way you can think of that, you know, is event is in here. I guess it's actually in one of these macros that expands here. I think it's in this one right here. We'll actually pull out like the bits, you know, for an event handle and check whether they're set the right way. So anyway, you guys can come look at this ID class later, but just understand that this is like the decoder table and how to figure that out. So let's actually go look at get gen event impl. All right, here, it's right down here. Okay. All right. So the first thing that we're gonna do, right, when we get our ID, we realize this is an event. You know, there's a nice assertion here saying this is an event handle, right? We need to look up the generational event data structure, and we'll talk about what that data structure does in a bit, but we need to look it up here on our local node, right? So the first thing we test is, you know, is the creator of this event the same node that I'm running on right now, right? And if that's the case, that's the really easy case, right? We can effectively say, you know, we can just look up and create a generational event data structure if it hasn't already been made, right? So in our local events, right, for this particular node, we can just, which is one of those dynamic table things that I showed you earlier, we can just create an entry if it hasn't already been made. This lookup entry is effectively saying like, check to see if we've already got a generational event data structure, and if not, make one, and then we'll be able to return that, right? And we use our, you know, event index, and this is our local creator node, so everything is local to this node, right? And if it's remote, right, one of the things that we actually have to do is you know, check to see, we look up in this node's data structure here, right? Remember that node data structure that I showed, or struct that I showed you earlier, effectively saying this is all the remote nodes, this data that we know about remote nodes, you know, get the one from whatever node, you know, actually made this event, and then do its lookup to get its generational event data structure. So this will like lazily populate, you know, this node data structure with events that it sees from remote nodes, right? And there's some checks down here, right? But eventually we're able to return this generational event data structure. So effectively, if it's local, we either find or make it, and if it's remote, we also find or make it, but we do it on the remote set of nodes to know that we're tracking something from a remote node. Okay, so now I've showed you how lookup for generational event data structure actually does. Let's actually take a look at what that thing is. So I'm actually going to keep this code open because we want to actually look through this event impl here. in just a minute, but let's actually, we're going to repurpose this id.h file here. Let's actually look into event impl.h. Okay, so what is the generational event data structure, right? So I told you that event is just a handle, and that's true for users, right? But a generational event data structure is actually the structure that represents the state of this event. In fact, it represents the state of all the generations of this particular event, right? And so it has a lot of the same methods that the normal event class does, but it also has a bunch more state associated with it, right? So effectively, there's a few things happening. The most important things here are some of these things here, right? So, this atomic is representing, what generation the event has most recently triggered, right? So effectively, events trigger in order, right? And you only, and so either your current generation is the one that has most recently triggered, which means you should only ever see handles for generation +1 while you're actually running. Generation subscribed applies to cases of this generational event data structure on remote nodes, right? So like if you make a generational event data structure on a remote node, just to show you this case right here, right? This is where we made a generational event data structure representing an event that's actually owned by a remote node, right? What you actually do is you do an operation called subscribing. And what that means is that, if you see an event from a remote node, you make a generational event data structure, and then you send an active message to that owner node to say, please tell me as soon as you know that this event has triggered, right? And we'll look at that active message in a bit. But this generation subscribed is telling you, up to what generation have we subscribed to notifications about the triggering of that event from a remote node. So like on the owner node for an event, this field doesn't actually do anything. But on remote nodes, it's actually quite important. Then we have some information about poisoning and stuff, and I'm probably not going to go into too many details about that. But these two fields are actually quite important. We'll talk about what some of these other things are down here, but you can see there's lots of additional things to see inside of this generational event data structure. Okay, let's jump back here. Okay, so we've actually dug out our generational event data structure, and you can see there's actually an event impl, which is actually the base class of this gen events impl, right? So I skipped over this part, but there's actually a class event impl, right, which is sort of a virtual base class that provides the generic interface for event impls. You can see it's inherited by both the generational event data structure for representing events as well as the barrier impl class for representing barriers. So that's the reason that you see that there's a base, sort of a virtual base class here for that. Okay, so we've got our event here, right? And we can do is we can actually do like a quick little query, right, of the current event. This is sort of like an atomic check of the current generation of this event, right? And this event impl generational event data structure will allow you to get the current event. Or actually, we're just pulling out the current generation from the handle, right? That's actually what this ID thing is doing here. So this ID is grabbing the handle for the event and then getting the current generation from it, and then we do a fast test to see if this thing has triggered, right? And if it has, we can actually return right away, right? Because in that case, we don't actually have to do all the work to block and other stuff if we can see that this generational event has already triggered. Let's actually look at this method here real quick. So I'm going to jump into event impl.cc. So that's the event has triggered. We actually want event impl has triggered, right? So that's this method here, right? And you can see we're taking the generation that we need, right, and also a boolean to say whether or not this generational event data structure has been poisoned, right? So we do a first fast check here, just using atomics, right? We can effectively take advantage of the fact that this generation member is an atomic, standard atomic, right, and do a load acquire on it. And if our current generation is less than or equal to the current generation, that implies, remember, this is the generation that is most recently triggered for this generational event, right? And so if the needed generation is less than or equal to that, that guarantees us that, this event has already effectively triggered, right? We need to do a quick test to see whether that was a poison generation or not, right? To look that up, but that's happening, like I'm not going to dig into that because that's very, very rarely the case, right? And so then we can return right away, right? Let's see. I might need to get Sean to explain this has local triggers thing. Or I will need to dig that up and explain what that is later. Let's ignore this case for now. Right, and so the common case though is like if you get here, right, what you need to do is you actually need to take the lock, and so the generation event data structure has a lock associated with it to lock all of its internal data structures, so you can reference it and so forth, or get atomic access to the internal members. Right, and it can see if there are any local triggers that are pending to this particular generation. If so, you can record that effectively it's been triggered. If not, then you're just going to return that we haven't triggered yet, right? And that will return false, right? So effectively, there's a fast path and a slow path, right? That will do both that will handle the various different cases of has triggered. Okay. Let's see. So if we didn't trigger, right, then the next thing that's going to happen is we're going to go and actually perform a wait for this particular event. And actually, I'm thinking we will probably not dig into this today because this actually involves digging into the threads and stuff, but this will actually cause the preemption of the task. So you can actually get the current thread for this task that you're running in and actually preempt. The one important thing I do want to show you, let's see if this is actually what I want to show you. This event triggered condition, I think that this is, let's see if that's actually in event impl.h over here. No. I actually wanted to show you this event triggered notifier, but that's actually a different thing. Okay. So yeah, so wait will eventually actually preempt this task and block and stuff, and this will return from this this call once the event has actually finished waiting. And I'm going to apologize because I'm not going to dig into this today because it involves actually digging into threads and stuff, and I'm trying to avoid that today. Okay. So I've shown you how to look up generational event data structures. Let's actually show you what happens when we trigger one. Since you saw how we tested for has triggered, let's actually look at how we do actually a trigger. So let's actually take a look at user event trigger here. So remember, a user event is something that the client can actually make and can then trigger when they're ready to actually trigger that particular event. So here's user event trigger, right? And you can actually even give a user event an event precondition to wait on, right, as part of the trigger, right? So the first thing we do is we test this wait on, and see if it is triggered, right? And if it hasn't triggered, if it already has triggered, right, we can immediately turn around and trigger the generational event data structure for this particular user event, right? And if not, right, we're actually going to defer this trigger, and I'll actually show you how that works in just a minute. But let's actually take a look at this gen event trigger method here. Okay, that will be over here in event impl.cc. If I can type. There we go. Okay, so what this is doing, right? We actually make a little handle for the event, the name of the event that we're actually triggering here, right? And this is actually where you actually start to see some of the multi-node aspects of Realm start to show up, right? So what we're going to do is we're going to go through and we're going to do our trigger and see if we need to notify any of these event waiter things, and I'll show you what the event waiters are in just a minute. Right, so let's handle the common case first, right? This generational event trigger could come in, right? And we could be triggering an event that was made on this node, or we could be triggering a user event that was made on a remote node, right? So the common case, right, is that we're triggering an event that was actually made on our local node, right? So we own this event. We're going to actually go through and do the trigger on this local node. And we'll talk about the case down here where we're not the local node in just a minute. Okay, so the first thing we do is we grab our lock. By the way, you'll see that Sean and I use the same methodology in both Legion and Realm everywhere. We try to do pretty much, this is a digression, but pretty much all locking in Legion Realm is done with these auto lock objects. We try to keep locking scoped lexicographically, on the stack. It's just much simpler. So when you see this auto lock, what that means is, you're taking this lock at the point where you construct this auto lock object. And then, as soon as this object goes out of scope, right, C++ calls the destructor for it. And in that destructor is where the lock on release will be done. So as long as this, as this object is in scope on your stack, right, then you're holding the lock. So anyway, you'll see this convention all over Legion Realm, and yeah, we try to do that for just for simplicity and making sure the code is sane. There are ways to release and reacquire the lock in the middle of your stack, but we use those very, very rarely, just for simplicity. Okay, digression over. All right, so we're triggering this event. You'll notice a little assertion here. I told you that you should only be triggering the next generation from the previously triggered one, right? So a little assertion to test that we're not triggering some generation that we're not expecting, right? We're going to grab the list of current local waiters, and we'll look at this a little bit later, but let me just conceptually tell you what it is. Effectively, anybody who has been waiting to be notified once this event has triggered, right, gets stored in this current local waiters data structure. And so, effectively, what we're grabbing is the set of things to notify that this event has triggered once we're actually done with the trigger, and we're going to take care of that later. So you can see we're going to put it in this this 2-wake data structure here, right? And so now we are going to update the generation, right? And there's a little bit of trickiness here because of some of the lock-free parts of the fact of how Realm works, the fact that you can actually query the generation kind of using the standard atomic, right? We're being a little bit careful of how we're doing some of those things. I'm going to ignore most of the poisoning stuff here, right? We're going to assume that I'm not going to talk about the case where we actually poisoned this user event instead of triggering it. At this point, we can actually store our new generation into the standard atomic that represents the current trigger generation. So once you do this, anybody who calls has triggered, without acquiring the lock, can actually see the effect that this event has triggered, right? This freeing event occurs. This generation event data structure can actually be cleaned up once it has triggered all of its generations, right? And so we're doing a little check here to see whether we've actually exhausted the set of generations or the maximum number of poisons that we can have in this data structure. This is pretty uncommon. Well, actually, sorry. I should actually say that's actually not what's happening here. This free event is actually saying, can we tell the runtime singleton for Realm whether or not we still have extra generations left and can be reused, right? So a generational event data structure gets reused for all the generations of an event, right, up to the point where it's exhausted all of its generations or it's filled up all the max poisons, right? And so, as long as we've still got more generations to go, right, we haven't hit that, 2 to the, I think it's 20 some, or 20 or 30, or what was it? I forget how many bits there were allocated to generations in the handle for the ID. But as long as we've got more generations to go, we go back on the free list so we can reuse this generational event data structure in the future. This is a special case for handling external waiters, which are if a non-realm task waits on an event, you just have to notify those guys special. Okay. And then importantly, I guess I skipped over this part, this to-update part, right? We actually grabbed the set of remote nodes that we need to notify, right? That may have subscribed to this this triggering of this generation or subscribed to this event, right? And so once we release the lock, by the way, you see this lock here goes out of scope with this matching pair here, right? So right here where this the scope goes out of scope, that's where the lock is released. And so you can see after we leave the scope, right, we've now released the lock, right? So the first thing that we do, if we had any remote waiters or remote nodes that had subscribed to this event, right, we will send them an active message to trigger this this event, right? So we actually make this this active message, and then we send it out to all of the different nodes to update, right? And I'm not going to talk about active messages today, but effectively this is, filling this in, giving the name of the event that's triggered, and then sending that out, right? Right, and you can actually see here, it's actually an interesting syntax here because you're making one active message, right? But you're actually sending it to lots of different places, right? So to update could be any number of nodes, right? And this commit will ensure that this active message gets sent to all the nodes in to update. And that will actually notify them those remote generational event data structures that the event has triggered, right? But the only way for them to get that active message, right, is they have to subscribe, right? So like effectively, like they have to subscribe, and then that's how things get stored in this to update data structure. I guess we can actually look at to subscribe if we've got time at the end of the talk today. We can free the event if we had some free space. Before we do the else case where we're not on the local node, if I scroll down here to the very bottom, you'll actually see where we actually notify all these event waiters, right? And you see, like, what we actually do is we get one of these event trigger things, which is effectively a background work item to actually do the triggering. And that's actually what triggered these event waiters. And if I actually show you, let's actually go take a look at event impl.h. Let me just show you how this works. So lots of things can wait on an event in Realm, and they all implement this abstract event waiter class, right? Has a couple of different methods to it, right? It can say like, this is the callback that these event waiter objects will get once the event has actually triggered. So inside of this, trigger event waiters, eventually, for all the waiters in here that were waiting on this event, we're going to go through and call this event triggered method, right? And that's effectively their callback to tell them that like the event has actually triggered and you should go off and do something else. So lots of things can implement this event trigger class. You'll actually see it all over Realm. Let's see if there's actually any in here, right? So here's an example of an event waiter for merging a couple of events together, right? So like effectively an event merger is like when you want to create a new event by saying a new event will trigger once, some number of previous events have all triggered, right? That creates an event merger. So an event merger, precondition effectively for any events that were in this merger that haven't already triggered, right? They create one of these event waiters and then record it with the generational event data structure to say, please tell me when, this event precondition has triggered. Here's a deferred destroy operation on a completion queue waiter, right? So, and this is just in this particular header file, there's lots of places where you'll find this public event waiter interface being used to record things on the generational event data structure. Anyway, there's also a useful print method in here. One of the things that we often ask people to do when Realm hangs is to actually dump out all the event waiters so that we can see like what is waiting on which event, and we have some actual tools that will actually be useful for debugging like hangs and stuff in Realm by looking at these event waiters and so forth. Okay, so anyway, one interesting thing that can happen here is one of the reasons that we don't just go through and trigger these things, these waiters immediately is that you might actually have a lot of them, and so you might need to do the event, the notification sort of periodically as like a group of background worker objects instead of just one set of background worker objects, or just calling all these, or just calling that that notification method immediately for all these objects. We used to find that like there was a performance bug in Realm where like if you just notified all these things immediately, in cases where you had a bunch of event waiters, you would actually have this event trigger method look like it took forever, like sometimes potentially even like milliseconds worth of time to do some of these event triggers, just because like there were so many things to wake up in some very unusual cases. So instead what we do is we effectively are putting these on background worker threads and chunking them up to make sure that they're more evenly distributed and we're not getting stuck or appearing to get stuck inside of this event trigger method. So I'll let you guys go look at that and understand what's happening there. Okay, let's actually take a quick look at what happens in the case where we're not on our local node. So remember, the first thing that we did was we hit this like, if we're on our local node, right, we actually can do the trigger here and then send out notifications, right? But if we're triggering, if we got this trigger method on a remote node, right, we actually need to do something different, right? So the first thing that we have to do, right, is check to see if we're doing this trigger, right? It should be the case that, we're way less than the generation triggered on this, or we're higher than the generation on the current node. Now note that this generation might actually be much less than the generation triggered because we may not have subscribed to intermediate generations in between, right? So the first thing we do is we actually make an active message, right? And we fill in the event that we've triggered, and then we send it off to that node, right, to the owner node for this particular event, right? So like the first thing we do is we send that active message, to the node that actually does own this user event and tell it to trigger, right? Which I'm not going to show you this today, but effectively this active message, when it's received on the remote node, will turn around and call this trigger event here, right? And it'll happen to end up this time on the local node, right? And do all the stuff that the local node does, right? So this active message is just sending that notification to the remote node, say, go trigger this thing, right? One of the interesting things that we can do, though, right, is we don't need to wait for that trigger to actually run through the whole process on the owner node before we can actually do stuff locally, right? So once we've kicked off that active message, now we can come into our local data structure, right? And we can actually do a lot of the same work that if we had waiters and stuff like that on our local node, right? We can actually grab those and actually are going to be able to trigger those locally, before we even have to wait for the notification to come back from the owner node that the trigger was complete, right? Because we know that the trigger has occurred, right? So we can actually go through and do all the stuff locally without needing to wait, right? And let's see, I'm going to ignore the future waiters here for a bit. We'll ignore the poisoning and so forth. Let's see. All right, remembering what happens here. All right, yeah, here's where we actually update the generation. What was this if statement? Let's see. Yes. So okay. Right. So effectively, we can only do this optimization in the case where, the gen triggered is actually our current generation that we know about +1, right? So it's actually not safe to do this optimization in the case where we're not the case, right? And so that's where these future local waiters actually come into play, and we can only trigger the ones that are from future generations. I will probably need more time to explain what is happening here than I have in this talk. So I'm going to encourage you guys to think this through and ask me questions offline about what's happening in this particular case. But suffice it to say that really what's happening is, when you subscribe on a remote node to if this generational event data structure on a remote node, it has stale information about what the trigger generation is. You can actually see waiters from a bunch of different generations in between, the currently triggered generation and the current generation that you're subscribing to, right? Because, the owner node could have gone through many triggers, but you've sent off a bunch of active messages to subscribe to those intermediate generations, but you haven't heard back from it yet. Right. And so effectively, because you can have stale state about the generation on the remote node, right, you can often have waiters from multiple different generations at the same time on a remote node. I shouldn't say often, but you can. And so this code is handling that case where you have stale generation information on a remote node and tracking which waiters are waiting on which generations and so forth. Yep. And one important thing that does happen here is you can also get these subscribe messages. So let's actually take a brief moment to talk about the subscribe, because I think it's actually important to mention what subscribe actually does and why and how it actually works. So let's say that we have a bunch of things that want to wait on an event on a remote node. So one of the things that let's actually go look at subscribe here. I'll say users can implicitly subscribe to an event, but they don't have to. Realm will actually do subscriptions for you. So we're actually going to look at generational event subscribe. You can always ask to subscribe to an event yourself, but you don't have to. Realm will do this for you if you wait on an event. So subscribe is effectively a way to deduplicate waits on a remote node, right? So if you have lots of things that are waiting on a remote generation, or on an event on a remote node, right? What we do is we actually deduplicate them. We store all the local waiters, right, in the generational event data structure on that remote node. But the first time that we get one of those waits, right, we send a subscribe message to the owner node for that event to say please notify us when this particular generation has triggered, right? So subscription sort of deduplicates that. It guarantees that you get only one request to see the update when the event does trigger, right? And then you get one response once the event does trigger back to this node saying like, hey, this generation has been updated and has triggered, right? So you can see here in this generational event data structure, the subscribe method to a particular generation, right? What we do is we look to see like, first off, if our subscribe generation is less than or equal to the current generation, well, then we've already triggered. So there's nothing to do, right? Otherwise, we can actually take a look at like whether this is a special optimization, whether we have local triggers. Like if, for example, the user had done a user event trigger on this local node, right? We might have seen that ahead of time, and then we can also know that we're already triggered. But if not, and our generation is less than the subscribe generation, remember I told you about the subscribe generation, right? Then we need to actually send the subscription message to the remote node, right? And then we can update this generation subscribed, right? And once we release the lock, right, then we actually send the active message to the owner node saying, please subscribe me to this particular generation of this event, right? And that's actually what deduplicates, all the waiters from doing the subscribe. So you can actually see, we actually call the subscribe internally here. Let's see if I can find it while we're down to the barriers. Let's see. Okay. Yeah, actually, let's. Where else do we send this active message? Event subscribe message. Oh, yes. Yeah, so you can actually see like, that was the trigger method. Trying to find the place where oh yeah, here it is. So remember I told you about these event waiters. This is where we actually add one of these event waiter objects to our generational event, right? And you'll see down here at the bottom, I'll look at this code in just a minute for you, but you'll see down here at the bottom, if you have to, you actually send the subscribe message to the owner node, right? If you're on a remote node, to say like, please subscribe me to this event, generational event data, or this generation of this event from a remote node. Excuse me.
Can I ask you about this generation check that was happening in the subscribe?
Yeah, you want to get back to subscribe? Okay.
So there was a check at the end there, right? So if not already, line 1639.
This one.
What is the logic here? So if it looks like if I'm that I need to send this message if I'm subscribed to if I'm trying to subscribe to a later generation.
That's
right.
Yeah. So
I'm not subscribed, right? But it sounds like I don't need to send anything if like I ask for an earlier generation because the subscription is good still.
That's right. Yeah, exactly. So like once effectively you're actually subscribed to all generations up to gen subscribed. So for example, like, and this is like a little bit of overkill, but effectively like the way it works is when you subscribe to a particular generation, like let's say gen subscribed is actually like 2. Right, and you're actually you want to see about generation 4, right? So the last generation that you subscribed to was 2, and you want to see when generation 4 has triggered, right? So what you do is when you send the subscribe message, that actually guarantees that this node will suddenly subscribe to both 3 and 4, right? So kind of implicitly, right? So whenever 3 triggers, you'll get the notification method for generation 3, and then it'll also get the notification method for generation 4.
Got it.
Does that make sense? Right.
Right. You might not need it, but you'll get it.
Well, and one interesting that might happen is like maybe you subscribe for generation 4, and what happens is, when the active message for the subscriber is arrived on the owner node, it'll say, oh, look, 3 and 4 have already triggered. It will only send one response message saying, like, the new generation is generation 4. The most recently triggered is 4, right? And then that'll turn around and trigger this generation event data structure for both 3 and 4 right away, right? Because, like, effectively, you can just bump the generation up to the highest one safely, right? Because they trigger in order. Does it make sense? So you can actually, it'll actually, deduplicate active messages, or like deduplicate event triggers messages, right, from the owner node. Okay, hopefully that made some sense. Okay, let's actually, I wanted to finish with that add event waiter. What was it called? Yep. There we go. Right, so yeah, and you can actually see this is the method where we actually record waiters on this generational event data structure, right? So I showed you this event waiter class, and we're going to see lots of examples of event waiters over the course of like looking at Realm. You'll see it occur over and over again in lots of different places. But effectively, there's a couple of different cases here that occur, right? Effectively, right? So this is handling the case where we've already triggered, right? If the needed generation is less than the triggered generation, then we're already done, right? So we can sort of trigger this thing now, and we need to know whether it's poisoned or not. But that's the easy case. Case number 2 is, we're not the owner node, but we already know that this event has been triggered. This is actually pretty rare, but it does happen where, like, if you've got a user event on a remote that was triggered on a remote node, and then you do a subscribe, or you try to add a waiter on that remote node, right? You can actually see that, it's already been had a local trigger be done here on this remote node, right? And third is we don't actually know, whether this event is triggered or not. So we have to put this waiter in this set of current local waiters, or in the case of like a remote node, right, you might have to put it in one of those intermediate generation, data structures, the future local waiters, right? Sort of handling the case where you've got a bunch of waiters of different generations on a remote generational event data structure, right? And then if you're a remote node, you got to check the subscribe thing, the subscribe generation, right? See if you've actually subscribed to this generation or not. And if you haven't, then you actually need to send that active message to actually do the subscription. Right, so the first time that you add a new event waiter on a remote node, you send the subscription node back to the owner node to say, please tell me when that event has triggered, right? And then down here we've got send off the active message, and down here we do, if we already triggered, then we can actually turn around and call. You can actually immediately call this event triggered method on this waiter right away, right? And again, be careful of like time limit, cases. Like we've seen lots of cases where like this waiter might have been like an merger, which then triggers a bunch of other downstream event mergers and stuff, and so things can recurse pretty far through these event triggered. Like sometimes, like if you got a big chain of things, like triggering one event, well, it's propagating those event waiters can send you down a giant rat hole, right? And so we have lots of guards inside of Realm to help make sure that like triggering of things doesn't take too long. So something to be careful of. Okay, so hopefully after this talk, you have a feel for like these generational event data structures and how they have this sort of state machine inside of them for, adding waiters and updating generations, and then sending out active messages and doing triggers and stuff like that. We're gonna need to look at a lot of machinery around these things, but in some sense, this is almost one of the most important parts of Realm, and this code gets beat on quite a lot because, right, these generational event data structures underpin all of the synchronization and stuff for Realm. And there are also barriers, but I think barriers are a much more niche case and not something that occurs nearly as often. So anyway, the generational event data structures are sort of one of the most important parts of Realm. And if you understand them, you actually understand like a good chunk of what's happening inside of Realm. So we've got a few minutes left. I'm happy to take any questions, or we can end a few minutes early.
So I have two basic questions.
Sure.
So the first one is like why we have generations for the event?
Yep. So the idea is that, events are just handles, right? From the user's perspective, right? Like a handle is just a name for an event. It can be passed around by value. Users can store it in the heap. They can serialize it in active message, or serialize it in messages or other kinds of stuff, right? And we don't care. They just kind of like show up, right? Like a handle to an event, right? Can be the user can do whatever they want with it. We have no limitations on it, right? And you don't want to have to, and they can just do whatever they need to do with it, right? And importantly, one important property of like Realm events is that they don't need to be explicitly destroyed, right? So you don't have to clean up an event handle when you're done with it, right? Like if you look at like CUDA events or something like that, you actually have to call like CUDA event destroy when you're done using that event. In Realm, there is no need to ever be able to destroy an event. Events are not garbage collected either by the user or implicitly by Realm, right? And the reason that we can get away with that is because we have these generational event data structures. And the way that we get away with that is that many events are all mapped onto one generational event data structure, right? In fact, many events, right? If we actually go look at, let's see, do we still have id.h up here? Let me actually pop it up real quick. Right, so how many generations do we have? We have 20 bits in every generation. So every generational event data structure actually stores the state for 1,000,000, right, 2 to the 20 events, right? And so what that means is that we can very efficiently represent lots and lots and lots of events using just a very small number of generational event data structures, and they never need to be garbage collected, right? So users can refer to events that are really, really old that map onto the same generational event data structure that, you know, that later events also map onto, right? And so users don't have to destroy events and stuff like that. So generational event data structures have lots of good properties that make them really efficient and, you know, and actually make the user's life much, much easier.
So otherwise, yeah, go ahead.
Generational events are flyweights, apparently, in design, flyweight design patterns, right?
I don't actually know that design pattern, but yeah.
Okay, so briefly, it means that you are abstracting away the representation, and many different objects refer to the same representation.
Yes.
Typically.
Yes.
Okay.
Yep.
Yeah. Sorry for interrupting.
Yeah.
Okay, so the events are actually very cheap, so user can create as many events they want. There's no like overhead.
Yeah, I mean, I wouldn't say that they're complete cheap, but yes, the actual storage space for them is actually fairly small, right? Like, I mean, to some extent, you always need to have as many generational event data structures as there are live events in the program, untriggered events. If let's call live events untriggered events, right? So you always need to have as many generational event data structures as there are untriggered events in the program, right? So if that number is actually really big, then you can still, like, making events is not necessarily cheap, you know, in that sense, right? So if you made like 1 billion user events, you would need to have 1 billion generational event data structures, right? If you made 1 billion of them before triggering any of them, right? But if you make like 1 billion user events and you start triggering but you only have like 1 million of them live at any one point in time, well, then you've decreased like the representation by like 1,000-fold, right? So effectively, it allows us to duplicate like you know, events that, you know, are not necessarily, don't have overlapping lifetimes, right, in their triggered and or between the points where they're created and where they're triggered, right?
Okay. So my last question is like, what does a poison mean to event?
Yep. So events can either be triggered or poisoned, right? Either one will bump the generation, right? A poison means that either a fault was detected or the user has explicitly decided to poison it. But, well, we can look at poison a little bit later, but poison will actually propagate through the realm event graph. So, like, if you poison an event, then anything that waited on that event will also be poisoned, right? And anything that, you know, if you poison like a task or something like that, that will poison its completion event, right? And that poison will propagate through the event graph and strip out any waiters and stuff and prevent them from running. Right, so poison is kind of like a way to instead of like having triggering ripple through the realm event graph and execute stuff, poisoning will ripple through the realm event graph and tear all the things out and make sure they don't actually run, right? Okay. Yeah, and yeah, it's a good way for doing predication or dealing with faults and stuff like that. Yep.
Okay, thank you.
So I have quite a few questions, but I don't want to extend this meeting. So where can we ask questions? Is there
I'm happy to go over.
channel?
I don't think anybody needs to. I'm happy to keep going if people want to stick around. People should not feel obligated to stick around past 1, so people can leave anytime. Let's get the questions answered.
Okay, so it looks like this subscription mechanism it's essentially an observer design pattern, correct? I'm just trying to fit in my mind to something that I know.
To some sense, yes.
Okay, and the nodes and events are essentially equivalent to actors and messages, right? If we were to talk about an actor model,
Kind of. So like, I agree that there's stateful objects and we're sending active messages. The thing that I think of actors method or actor programming models as like method dispatches implicitly messages, whereas here we're actually sending explicit messages in various particular places. But you're right in the sense that like what we're doing is we've got like stateful objects across a bunch of nodes, and we send active messages between those stateful objects, right? And each of those objects has a state machine that handles stuff that's happening, handles messages that come in and does stuff, and then sends out its own messages and things like that.
I see.
But yes.
Yeah, from the code organization standpoint, so I see, is there like a pimple idiom is being used a lot? You separate the implementation or the bridge design pattern, right? Is that what's happening with the implementation? Do you use like an opaque pointer to the implementation inside that you hide then?
Right. Yeah. I mean, we try to keep everything on the client side as being done with handles and stuff like that, as opposed to referring to pointers and things like that. Right. And we look up the actual data structures from the handles. Right. So that.
Yeah. So using that, you can do even type erasure. So I was wondering if type erasure is something you consider, or.
To some sense, yeah. I mean, you could conceptually store a lot of these handles like just as the base ID, right? Like this ID handle, right? And then the types are actually encoded in the IDs themselves, right? So you don't actually strictly need things, but we do try to keep some sense of type checking. But yeah, I mean, conceptually, you could get rid of like all the actual types on the handles and just say they're all an ID type, and like we can look up the type from like the tag and stuff like that. So. But so we do try to keep some type sanity here. So yeah.
So you have a runtime dispatch mechanism somewhere based on some tags runtime tags.
Well, we actually, I mean, the way to think of it right now is like when you have an event handle, right? It has an ID, and we're assuming that if you've cast it as an event, that it actually is an event. But we often will check that the tag actually matches the type that you say it is, right? But yeah. So we do try to keep with the C or C++ type system, but we do some sanity checking at runtime that you haven't done some typecast that was unsafe or anything like that.
I assume the talk about handlers and user-provided handlers, that talk is going to come later, right?
We will talk about the active message interface a little bit more. And like how active messages work in Realm. Right now I'm hand waving a bit and saying like we can send active messages between nodes and they get received, but I haven't shown you how that actually works yet.
And I noticed that classes are not templatized. There are no templates being injected as policies. Is that on purpose by design? You try to avoid static polymorphism? Okay.
Oh yeah, there's a couple places where templates are going to exist in Realm. In particular, when we look at index spaces, looking at dimensionality and stuff, we'll see some templates there. But in general, like I think we try to stay away from template stuff. And at least at this level, like with everything being handles, there's not really any need to template anything.
For example, the C++ actor framework, they're taking the exactly opposite approach. They're templatizing and using static polymorphism. Anyway.
Yeah.
So I noticed you're using this swap mechanism in quite. Is that a substitute for move semantics?
You're probably also seeing some artifacts of the fact that like Legion Realm had to support C++ 98 for a very long time, and only recently have we moved to C++ 11, right? So,
Okay, so that is what the swap
you could probably I mean swap was like moved before you could actually do that, right? So,
actually that's what triggered move semantics being included in the standard. It's Herb Sutter's trick. Okay, and looks like there's some oversubscription happening, right? Because if your current load of 2 and the actual load is 4, and then you want to subscribe to 4, you also subscribe to 3, but
that's right.
That might not. So I was wondering, is there any opportunity for performance optimization there?
You could. I mean, I think we definitely are making a trade-off. You're right that we effectively are oversubscribing to intermediate generations, right? We might get notifications that we don't actually need, right? We might get a notification active message for like generation 3 that we didn't actually need. We didn't actually have any waiters for, right? And the thinking is just that, it's more of a simplicity argument, right? Like effectively, if we want to track like on the owner node, like the specific generations that each remote node had waited for, right? We could do that. It's just more complicated, right? And it's just simpler to say like the remote node has subscribed up to generation 4 as opposed to saying it's subscribed to generations 1, 3, and 4, right? And so it's just a simplicity thing, and it hasn't caused too much overhead as far as we can see yet.
And lastly, 2 very humble suggestions. I was hoping at some point, maybe in the beginning, it would be nice to hear about the history of the dynamics between these 2 pieces of code, Legion and Realm, number 1. And number 2, talking about Regent, I think it's important to give a satellite view of that Regent, I think, has of where these concepts are coming from and how high abstract they are.
Yep. Yeah, I mean, we're way down in the details here of like how the Realm runtime works.
Yeah, for a newcomer like me, especially, we at least looking at Regent was very
right. Yeah, and I should say I mean, Legion Realm co-evolved together at the same time, but Realm has always been designed to be more generic than Legion, and designed to be sort of a generic interface for low-level systems beyond Legion, and it's had some success in doing that. And so
I thought Legion it sits on top of Realm.
Legion sits on top of Realm, but Realm is more general. You can build things in Realm that are not like Realm is a more general distributed system and has a more general but lower level programming model than Legion, right? It's much more explicitly parallel, much more detail oriented, right? You have to handle a lot of details yourself, right? If you program to Realm directly, but you can express computations in Realm that are not that don't have sequential semantics like you need in Legion, right? Realm, you can start up a bunch of different tasks in different places, and then they can spawn their own tasks, and right, you don't have the inherently sequential program that you have in Legion, right? So
I see.
Yep. So
thank you.
Yep.
Hi, Mike. Maybe Poison is not exposed in Legion programming interface. Is this understanding correct?
That's right. Legion uses poisoning mostly for predication at the moment. But you're right. There's no way to explicitly poison anything in Legion. There's a hook in the Legion API for reporting a fault, I think, but it's unimplemented at the moment on a logical region, on a physical region. So there's a way to create a fault in Legion that will then, eventually trigger poison to propagate through the realm event graph, but you wouldn't explicitly poison something on the Legion side.
I see. Thank you.
And yeah, we also, if you predicate something and your predicate, eventually resolves to false, then that will turn into like Legion using poison to actually prune out the part of the realm event graph that was predicated right on that predicate.
Actually, I'm very excited about some real usage of predicate. Have you seen any real applications using this new feature?
I know for certain that that Snap does use the predicated execution.
Oh, cool. Thanks.
Mike, can you give an example of when an event is triggered on a node that is not the owner of the event? How does that happen?
Yeah, I mean, the most obvious case is a user event. So let's say that I make the event a user event on node 0, right? And then I package up the handle for that user event, right, in an active message, or in some kind of message to a remote node. It gets serialized up somehow, right? And eventually it makes its way to like node 2 or something, right? And then the trigger is performed for that user event on node 2, right? And I mean, Legion actually uses this pattern pretty frequently. It's often the case that Legion will actually make a user event on one node and then trigger it on a different node, right? And so then you get the trigger message occurring on that remote node. Internally, I think Realm also may do some stuff like that inside of the DMA system, where like, right, it might ship like the actual copy control over to a remote node and eventually need to trigger the completion event for like a copy from a remote node.
Mm-hmm.
Yep.
So the copy operation might be initiated. I mean, the request might be submitted on node, let's say 0.
Exactly.
But
yes.
then Realm sends a message to node 1 and says, hey,
do this copy.
And,
exactly.
And let me know.
Yeah. In particular, like you could imagine, it's not often the case, or I guess not often, but you could get a case where like you're issuing a copy between node 0 and node 1, but the copy is issued from node 2, right? And so you don't want to do that copy on node 2, right? The control logic either needs to be on node 0 or node 1, right? And so you send that copy information over there, and then the event trigger will come from that remote node wherever the copy is done.
Right. And you said that when you want to trigger an event, you check to see if an event that this event depends on has already been triggered as well, right?
Yes. So in the user event case, right? Like, let's see if I still have that up. Right. Or actually, you wanted to see the user event version, right? You can have a precondition on the user event trigger for some prior event, right? In that case, actually, that's down here, right? You can actually create one of those mergers and then, effectively only trigger that merger, like once this event wait on has actually triggered, and that'll actually trigger this generational event, right? So, yeah.
And its dependencies on one other event directly.
That's one other event directly, but this event could be like a merger of several other events, right? So like you could have.
Could be the merger. Okay.
That's exactly. So you can effectively, right, like with event mergers are general things that like, you can take any number of events and turn them into a new event that will trigger when all the previous events are triggered, right? And then that could be passed as the precondition to this user event trigger, right? So, yep.
Thank you.
So when event let's say when an event from node 1 makes its way to node 0, then who's responsible to handling that event?
Well, it's distributed, right? That's what their generational event data structures on both nodes, right? Right. So the node that created the event is still considered the owner per se, right? But you might have, if you wait on that event, like on the remote node, like node 1 or whatever, right? Like then you can store waiters on node 1, and then you send one subscription message from node 1 to node 0 saying, please tell me when this generation has triggered.
Right. So it depends who's waiting on
That's right. And it's lazily constructed, right? It's only when the user actually, waits on stuff that things subscribe, right? So like you could pass that handle around all over the machine, but only on the nodes where you actually wait on something will it actually matter, right?
But you mentioned before that node 0 is sending back some information to node 1 saying, look, I received it.
Well, it only sends a message back once that generation has triggered, right? So like, so it doesn't send an acknowledgement. We're assuming that the network is like reliable, right? That like our active messages actually get there.
It just says I'm done.
Yeah, that's right. It says when this generation triggers, you'll get a message out to all the subscribers saying, hey, like this event is triggered. Like now you can do whatever work you need to do for any waiters that you've got, right?
Being handled is equivalent to trigger, right?
Yeah, I think so.
Yeah. Okay. Thank you.
So should we avoid like trigger doing the remote trigger, like the copies, like we're doing copy from node 0 to 1 on node 2. So should we minimize those operations?
Part of the part, I mean, not necessarily. I think it actually works pretty well either way, right? Like the point of Realm's API is that you can do anything from anywhere inside the machine with these handles, and Realm will do the right thing. I actually think that like just issuing the copy from like the example of issuing a copy between node 0 and 1 from node 2, right? it's actually probably faster just to do it that way, because like the alternative is you're going to send some sort of like message between the nodes using tasks, which are higher level, more expensive things than like the active messages, right? So Realm is probably more efficient sending the active messages itself, right, under the covers than you are doing it above on top. So it's better just to issue that copy between those two nodes from like node 2, right, and let Realm do the lower level active messages for you to actually make all that work.
Okay.
And then another question might not be actually straightforward to answer, but in most use cases, would you say for an event, there are many subscribers that need to be notified when the event triggers, or there are usually a few? I know
usually a few. It's usually a sparse set of all the nodes. So like I think the common case will be that you got, I mean, the most common case is there are no remote subscribers, right? And the second most common case is probably one subscriber, right? And then you'll have a few with a few subscribers.
I personally didn't know that you can actually dump the event graph for debugging. That would be actually very useful, I think.
Yeah. I'll show you where that is. Well, I got everybody here. So over here in Runtime Impl, there's the show event waiters. Yes. Actually, let's see where this is called. It's actually called from somewhere else. Yeah. So there's this static method here, realm show events, and you can give it an optional signal if you want to. But effectively, like if your program freezes, if your realm program freezes, and you can actually like go into like a debugger on every process and invoke this method, and it will dump out all the show event waiters either to standard out if you haven't filled in this environment variable name, or it will dump it to this to the file stored in this this environment variable name, and that will allow you to actually dump out all the waiters that are waiting on all of the generational event data structures inside this node, so you can actually see them. And then under the tools directory over here, let's see, let me find the name of the, nope, I lost the, I guess it's over here. Yeah, it's in, yeah, so this detect loops script over here will actually parse those event waiter data structures. You just give it the names of all the files, and it will parse all of the event waiters on all the generational event data structures and actually look for cycles in them to see if you've got like if you've created a cycle in the event graph or something like that. But it's also useful just to print them all out and look at them and see what's actually going on. So, yeah.
Got it. Thank you.
So the print events will print all events, not just the local one, right?
It will do all of the generational event data structures on a node, including the remote generational event data structures, but it will not send any messages to remote nodes to do it. So you've still got to go to all the processes and call the method on each of the processes.
Okay.
Okay. Any more questions?
I remember the event can be recycled, right? Through event ID.
Well, that's the generational event data structure, right? So like as soon as you free up, see if I still got it open. It doesn't look like it, but right. So it's gen event impl trigger. Where'd it go? Here it goes. Right. So right here's the. So as soon as this event has this generational event data structure has triggered this generation, right? As long as you've got more generations still available, right, in the number of generations in the ID, right, then it can be freed, and that free list puts this generational event data structure back on the free list of like I can be used to represent another event now because my previous one has triggered, right, and then when like Realm needs to allocate a new generational event data structure, like if you make a new user event, it'll go through the free list on the runtime and pull out the next generational event that is free to represent the next event.
I see. So, but what if we want the subscribe active message arrive late, and this event has been already like
Right?
triggered and recycled?
That's totally cool because, right, the generational event data structure still exists, right? It hasn't been deleted, right? And all that's changed is that, the generation has been bumped, right? And so, like, if you tried to wait on it, or I guess, like, let's look at has triggered. We don't want the barrier version. We want the event, yep. Right? It'll look up that same generational event data structure, even though it's been recycled, it's representing a new event now. But like when you do this check, you'll notice that your needed generation is less than the current generation, right? Or less than or equal to. And what that means is that event has already triggered. So you effectively, you can still reference it still works correctly, right? It'll just notice that like, hey, the generation has already been triggered, so I'm done.
I see. Okay.
Right?
Got it.
Because like you're right, it still refers to the same generational event data structure, which is now representing a new event, but that's okay because like you have all these checks on the generation, and you'll notice the generation you're looking for is old compared to the current one, and therefore you can infer that it's already been triggered.
Got it. Okay. Thanks.
And you can never have a wraparound kind of case.
That's right.
Because of that check that you had, right?
That's right. Yeah, generations only move in one direction. They're monotonically increasing until the point where you hit where at some point, once you fill up all the, right now it's 20 bits that are representing the generation, right? So you can have a little bit more than 1 million generations, right? Once the generational event data structure has done its million events, then it just kind of sits there for the rest of the run. And you don't ever delete it. It's always sitting there, but it's not being reused, right? So technically, it's kind of like a memory leak, but in practice, like we find that we hardly like ever see memory overheads from like the number of generational event data structures continuing to increase unbounded. So
right.
Yeah.
That's actually is very interesting.
Yeah.
How you are using this efficiently.
Yep.
Pretty cool idea.
Yeah, and you can play around with these bit mappings if you wanted like more generations per generational event data structure and. Right, to the 16 nodes, what is that, 16,000? Or no, it's 65,000 nodes right now. So like we're probably being like a little overly conservative on the number of, like most applications probably don't need 65,000 nodes, right? So, so like, we could probably like reduce that for some and like put some more bits over here in the number of generations to reuse generational event data structures for long running, or for applications that have fewer numbers of nodes and stuff like that, so.
Hence the name flyweight. It's a very cheap representation of opaque representation of something more expensive.
Yep.
That doesn't. Yeah.
Yep.
And are events the only kind of objects that you handle this way in Realm, or?
No, I mean.
Idea for other things.
You mean by the generational event data structure? You mean?
Mm-hmm. Yeah, something like
this. Yeah, because most of the other things are actually stateful and actually don't have the compact representation. The one other one that will represent like this is the barrier. Barriers have the barrier event impl, which we didn't look at today, will look very similar to the generational event data structure. But the rest of these things actually have like statefulness to them and stuff, and they don't go through generations the same way. Yeah. You can see we use bits for other stuff down here, like, for like memories, you can see like, we can figure out which owner node is owning this memory, and then, what its index is, like for the name of the memory object in that particular node, right? So, and then we've got a bunch of unused bits here in the middle, so. Okay. All right. No more questions. I think we'll call it for today. Thanks everybody for coming. We'll be back to Legion next week.
Thank you.
Okay. Bye.
Thank you. Bye-bye.